Hello, everybody. It's me again, Rich Andre, and today we're going to be talking about the general rules for electron configuration. So I'll just list them all. So general rules or principles for electron configuration. So when we're talking about electron configuration, we're just talking about okay, we're trying to assign sort of arrows and sort of orbitals of the electron on the atom. Okay, so we're trying to sort of predict the electron's movement in the atom. And there are three principles that we need to always follow whenever we're doing this electron configuration thing. And this first is called the Afbau's principle. So what is the Afbau's principle? Let's say we have this configuration right here. We have three lines here and three lines here. We have let's say 1s, 2s, 3s, and then 2p here. For all of these lines, this is 2p, and for every single line here, it for every single line as it is ascending, as is the energy levels of the sort of the orbital of the electron. Okay, so now that we've got this sort of diagram for our electron configuration, okay, and by the way, I got this idea from the organic chemistry tutor. So the organic, I'm basically just a rip off organic chemistry tutor, but I just took it from this video, so credits to him. But aside from that, okay, we're going to be talking about the Afbau's principle. And the Afbau's principle basically just states that you have to put an up arrow in every single line here. Let me just. One S, two S, 3S, 2P, bang, bang, bang. And then we have to put an up arrow for every single line, and then a down arrow before we move on to the next sort of path. Okay, so before we move on to the next, but those two pairs, okay, those two pairs of sort of electron orbital spin, okay, there's electron orbital spin. You need to put a down arrow before you ascend to the energy levels. Okay, before you ascend energy levels. So if you have something like this, if you have this sort of paragraph, diagram right here, you need to put a down arrow, up arrow first, and then a down arrow before you go upwards. Okay, but if you have something like this, before the highest energy level of the orbital spin, you need to, okay, you need to fill those up first before you go to the very top of this, to the very highest energy level. And now, okay, this is going to be this whole thing, okay, this whole thing that we drew here encompasses sort of like the basic gist of the Afbau's principle. Okay, you have to put up arrows and put two pairs of arrows first, one up and one down, before you move up an energy, on the energy, okay, on the energy levels. Okay, so now, okay, now we're moving on to this part. Okay, so you can see that there are three sort of lines, underlines here. Now you would think that we can just do this. We could just put an up arrow and a down arrow on every single one, and then move on to this. But no, that's not how it works. Okay, and that's where the Hund's rule Okay, the Hund's rule basically comes in. So what is the Hund's rule saying? Okay, though before you put an up arrow, you always put you if you have three sort of parallel spins here. If you have three parallel spins, you need to put an up arrow first on each single one before you put a down arrow. Okay, because if you put an up arrow first and a down arrow afterwards before you move on to the next sort of spin, then the electrical spin or the electron spin or orbit here would be unstable. Okay, so that is the gist of the Hund's rule. Okay, that is basically what the Hund's rule is. You can't put a down arrow on after you put an up arrow when you have this sort of like paradigm here. If you have like sort of this pattern here, you have to put the up arrows first before you put the down arrows to pair with them. And then we come to the last, okay, sort of principle that we need to follow in electron configurations, okay, which is the Pauli's exclusion principle. So what is the Pauli's exclusion principle? Suppose you have this diagram here. You have this same diagram. Now you can see the tree S is basically the missing one here. Okay. After you've considered everything, okay, now that you have that, now that you've finished the diagram, we need to talk about the Pauli's exclusion principle. What does the Pauli's exclusion principle basically just describe? Okay, so it basically just says that two electrons, okay, two electrons cannot have the same four quantum numbers. Two electrons cannot have the same four quantum numbers. And what are those four quantum numbers? Okay, the four quantum numbers that we're specifically referring to is first is n. Okay, so n in this scenario or in this context basically just denotes the general quantum number. So what does this general quantum number basically denote? Okay, what is this general quantum number? Okay, hold on, sorry about that. That was actually the principal quantum number. Okay, I got the name wrong. It's actually a principal quantum number. So what is the principal quantum number? Okay, the principal quantum number basically just says the size. It basically just describes or denotes the size and the energy levels of a specific orbit. Okay, a specific electron orbit, or where the electron is found. Okay, so it says here the principal quantum number n indicates the shell or energy level in which the electron is found. So that's basically what I said. The energy levels, it basically just describes the size and the energy levels of where you would find the electron. And you typically find the electron in the SPDF orbitals, which look sort of like this. So this, let me just draw it. So this S orbital, when we're talking about electrons, okay, where electrons might typically be generally found, the S is basically a sphere. Is a sphere, and if you would imagine the atom here, and then you have a S orbital. Then this will be the orbital, just a sphere. Okay, so that's where you would find inside that. That's where you would find the electrons. Okay, and you would also find, you would also have the p orbital. Okay, p orbital. It kind of looks like this. Okay, it kind of looks like this. It's like a bow. Okay, and the p orbital is basically just where you can find the electron. SPDF is basically like uh sort of like an illustration on where you can generally find an electron, because you can never pinpoint where an electron is, and that is the biggest problem in quantum mechanics. Because in quantum mechanics, when you are dealing with very small things, you can quantitatively sort of you can quantitatively estimate or guess where a certain particle, no, where a certain atomic particle is precisely. Because unlike big objects, okay, we can't accurately predict atomic particles, because they are very sort of, they are very jittery. And if you know Schrodinger's cat, if you've heard of Schrodinger's cat, wherein Schrodinger basically has this like this thought experiment. Erwin Schrodinger, okay, so he's a physicist, and he basically had this sort of thought experiment where you had where you had a box, and then you had a cat inside it, and then he plays basically just like this radioactive sort of device, and then it's basically like guessing if you never looked at the cat, if you never looked at the cat inside the box, you would never know if it's dead or not. And that's basically the same principle that applies to atomic particles. You never know where an atomic particle might be. So you can basically just sort of like have this conclusion of superposition. So what is superposition? Okay, so superposition, if you watch my other video on superposition in position in waves, the same principle applies. The same general principle applies. Superposition can happen anywhere. Okay, but it's a very small sort of subset of things. Like for for anything quantum physics. Okay, for quantum physics, you can apply the superposition principle. So what is superposition? So let's imagine you have two waves. You have sound wave, and then you have an X-ray. Those sound waves and the X-rays, if they sort of like have like the perfect sort of environments, have those two collide, they won't. They won't collide, and they won't sort of bounce back from each other. Those two will be at the same place at the same time. Okay, those two can be at the same place at the same time, covering the same space, covering at the same time, and that's basically what the superposition principle is. So, never mind that sort of abstract side tangent that I did. Let's go back to the topic at hand. So we have the orbitals, which are basically like, if you could think of it as a four-leaf clover, they're basically like this. Okay, this is basically where you can find the electrons. Okay, at a sort of given time, and also we have the F, which is multi-lobed. It is multi-lobed. There is a lot of lobes, like a flower petals. Okay, like flower petals, or sort of like you can see them as like d orbitals, but evolved. Those are what f orbitals are. Okay, so they can either be s, p, d, f orbitals, or whatever the electrons are so pleased to do. Because you can, as I said earlier, you can really never predict where an electron is going to be, or going to be located in a certain place at a certain time on an atom particle. On any single atom particle that you can possibly imagine, from the periodic elements of periodic elements table. Okay, so so now that we've talked about the principal sort of quantum number, let's the other property, the other three properties, or the other three quantum numbers that we're going to be talking about is the second one is basically like L. Yes. So the second quantum number that we're going to be talking about is the quantum angular momentum quantum number. That is a very big word, right? The angular momentum quantum number. Okay, so I'm going to explain it very simply for you. The quantum momentum number basically just says what what type of orbital. Okay, so we discussed what orbitals are, the SPDF orbitals. It basically just says what kind of orbital an electron is going to take place, or what kind of orbital an electron sort of orbital has, or what kind of orbital the electron is taking place in. So that is what the angular momentum quantum number is. Okay, it basically just like quantitatively describes the orbitals of the electrons. Okay, so that from my own understanding, but the third, okay, the third quantum number that we have is called the magnetic quantum number. The magnetic quantum number, okay, it basically just says, no, it's an ML, ML, it's an ML, okay. So the magnetic quantum number, it basically just says, and it represents the orbitals of a given subshell. So if you can imagine the orbits, if you can imagine the orbits of an electron, you could see that this is an atom. Whatever atom that you please, let's say a hydrogen atom. So we have one proton and one neutron, and then we have the orbitals right here outside here. It basically just says you have the let's say you have this shell, okay, and inside that shell there will be another shell. That will be the subshell. That's what we call the subshell. So it basically just represents any subshell, the orbital of a given subshell. I could be wrong on the subshell part. Okay, I could be. It could actually be like another subshell like this, like another shell like this, and then we could say that is a subshell. I'm not really sure, but yeah. So the third one, the fourth one would be the spin magnetic quantum number, or MS, M sub S. So the spin magnetic quantum number can only have a value of either plus 1/2 or minus 1/2. Okay. And the spin quantum number basically just describes the electron spin. Due to the spinning of the electron, it generates a magnetic field. In general, an electron with a spin magnetic quantum number of plus 1/2 is called an alpha electron, and one with a spin magnetic quantum number of equals to negative 1/2 is called a beta electron. So if you can see here from the diagram again, let's go back to the diagram here. If you have see, we postulated, or we described the diagram as going up in energy levels as it goes. So as we ascend with the sort of like the orbitals here, if we ascend the orbitals here, obviously the energy levels are going to go up, right? So if we have here, okay, and the same, so we can sort of have a connection here. If we have the spin magnetic quantum number, and what it basically just says is that it postulates or describes the electron spin. And whenever there is a ms equal to 1/2, that is called the alpha, okay, the alpha electron. So if you see here, you can see here, right? As it goes, you have, if you have something like this, if you have an up arrow that has like this is a 1/2. This is 1/2, positive 1/2. But if you go down, okay, if you go down, This would be, I believe, negative one half. This would be negative one half. So they basically just varying. If you go down here, they basically just have negative one half of electron spin. Basically just varies with the energy levels as it goes down and as it goes in a sense. So that is what we're talking about when we're talking about the magnetic spin. Okay, so given those four sort of like general quantum numbers, given those four general quantum numbers, we can say that the Pauli's we can now define what the Pauli's exclusion principle is. So what is the Pauli's exclusion principle? It basically just says that no two electrons, if you can imagine that these are two electrons right here, that no two electrons can have, okay, at the same place, okay, no two electrons at the same place can have these four quantum numbers, okay, can have all of these quantum numbers. So if we translate that into a simple day-to-day analogy, let's say we have two people, okay? Let's say this they're both named Rich Andre. These two people are both named Rich Andre. Now using the Pauli exclusion principle in this analogy, okay, we can say we have like four sort of quantum numbers, and those quantum numbers can be translated to sort of like let's say country, a country, state, city, and name. Okay. Now both of those Rich Andres can be in the same country. Okay, they can be in the same country. Let's say the United States. United States. And then the same state. Let's say San Francisco. No, that's actually a city. My bad. Okay, so let's say we're in the same state. Detroit. Let's say Detroit. We're in the same state, and then we're in the same city. Let's no 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 let's just say our state is New York. Let's say we're from New York. New York. U.S. states. We just I know New York is New York a state? I don't even know. Yeah, New York is a state. So let's say we're in both the same states, New York. We're both from New York, we're both from the United States, and we're both from the city of Manhattan. We're both from Manhattan. See? And hold on. No 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 no. Let's say gender. Okay, let's say gender. Let's just replace name with gender. So we're both from the United States. We're both New York. We're both from New York, and we're both from the city of Manhattan. We both have the same names of Rich Andre, but our genders aren't the same. We are the first Rich Andre is a male, and the second is a female. So that is what the Pauli's exclusion principle is. You can have all the same sort of like quantum numbers, but at least one has to be different. Okay? At least one has to be different. When you have two electrons, okay? You have two electrons in a certain spin, okay, in a certain sort of orbital. At least one quantum number has to be different from the other. Okay? So that's basically the general rules for electron configuration. We've basically tackled Afbau's principle, Hund's rule, Pauli's exclusion principle, and hopefully you got the gist, you know. Hopefully you got sort of like a basic understanding for this introduction of electronic configuration. And if you like the video, subscribe, give me a thumbs up. That would help a lot. If you didn't like the video, go ahead and give me your objective, constructive criticism and factual. Make it factual. Like I want it to be actually factual. Okay. So, if you think that I made sort of like a mistake in my explanations, you can go ahead and tell me, so we can fact check it. But thank you guys for watching. See you guys in another video.